Okay, so we're going to talk about relative extrema and absolute extrema. Actually, I think today we're just going to talk about relative extrema. And by extrema, what I mean is relative minimums and relative maximums. And this stuff is in section 4.2 and in section 4.3. Okay, so here's the definition of a relative maximum, right? We've got a relative maximum at some point x naught if there is an open interval containing x naught on which f of x naught is the largest value. That is, f of x naught is greater than or equal to f of x for all x in that interval. So if you're looking in the immediate neighborhood for those points around x naught, right, the value of the function for all those points around there is less than or equal to the value of the function at x naught, right? So you get a relative max if f of x naught is greater than or equal to f of x for all those other points. Likewise, f is said to have a relative minimum at x naught if there is an open interval containing x naught on which f of x naught is the smallest value, right? That is, f of x naught is less than or equal to f of x for all x in the interval. So when we're talking about maximums and minimums, we're talking about the value of the function. Where is it the biggest and where is it the smallest? And so let's look at these relative extrema, these relative max and relative mins, sort of graphically. I think it's easier to understand what's going on here. So they've got a couple points here. Here's a highest mountain, and here's a relative maximum. So this highest mountain, you can consider that's the absolute maximum. Over this interval, right, that's the highest value of the function. It's the highest point, basically. The relative max now, that's not the highest point, but it's the highest point in that immediate neighborhood. So say if you looked at the interval, this would be maybe x naught right here. So this point is x comma f of x naught, right? So the value of the function f of x naught is bigger than the value of the function for any of the other points in that interval. That's what they mean by the relative maximum. Now there could be plenty of relative maximums. This point's a relative maximum, that's a relative maximum, that's a relative maximum. All of these points, even the absolute maximum, is considered a relative maximum. All these points and some more, I didn't label them all, right? These are all examples of relative maximums. Relative minimums, right, are these points here, the points at the bottom of the value. It's the smallest point over a particular interval. So if in this case, we could call this point x naught. And if you look in the immediate neighborhood, right, some interval around x naught, the value of the function here is smallest at x naught. It's got the smallest value for these. Okay. So we get relative max and relative mins. They occur, if they occur, they're going to occur at what we're going to call critical points. And I'll talk a little bit more about what critical points are for this. But let's take a look at under what conditions we have relative maximums and relative mins. And this sort of takes us back to what we were talking about in section 4.1, the increasing and decreasing. Look, here we've got a relative maximum at x sub 0. So I'm going to write that out just to be clear. So we get a relative max of f of x naught, right? So the maximum is always the value of the function. But you'll hear it termed sometimes you get a maximum at this particular point. We're saying we get a relative maximum at x sub naught. So look what's happening. Immediately before this function, immediately before this point, our function is increasing. Immediately after this point, our function is decreasing. This point, right, where you get that relative max, is called a critical point. So look to this next diagram. We've got another relative max, right? Here's a relative max. Again, you could say the relative max is f of x naught at x naught. But look what's happening here. Our function is increasing before the point, decreasing after the point. It's a critical point. So we call this a critical point. This is an example of a stationary critical point. And this is an example of a non-stationary critical point. I guess I'm going to have to define what critical point is, so I'm going to go up here. So a critical point is a point where f prime of x is equal to 0, or a point of non-differentiability. Basically, you could say that f prime of x doesn't exist for that value. Right, it's undefined in many cases. I left a little space in there because when you've got a critical point, right, and it's a point where the derivative is equal to 0, that's called a stationary point. So when we look over here, this is a stationary point. Look, you get a horizontal tangent line drawn in there, right? That's a stationary point. You can think of it, remember our first derivative is our rate of change. It's stationary because if the first derivative is 0 at that particular instant in time, or at that particular instant on the graph, or at that particular point on the graph, the instantaneous rate of change is 0. It's not changing. It's stationary, just for that little microscopic blip. So this is an example, like I said, an example of a critical point that's a stationary point. This one's an example of a critical point that's non-stationary, right? You don't get a horizontal tangent line there, right? In fact, you get a sharp corner, a cusp, right? That's a point of non-differentiability. There's no derivative for there. So, but, you know, the function is still continuous there. It's increasing beforehand, it's decreasing after, so you're going to get a relative max. Okay. Let's look at the relative mins. Right? Look what's happening for the values of x immediately preceding x naught. For this one, our function is decreasing up to that point, and then after that point, it's increasing. Again, this one's a relative min. It's a critical point, and it's stationary, right? Because we get the horizontal tangent line, means the derivative is equal to 0. For this one, right, it looks like an absolute value curve. Again, our function is decreasing immediately preceding the point, it's increasing immediately following the point, right? X naught is going to be a relative min, or you get a relative min at X naught. I'm going to write that, at X naught, right? And that's a critical point, but a non-stationary one, right? Because, again, it's a point of non-differentiability. Okay, so know what a critical point is. That's really important. It's a point where your function may change direction, right? So it's increasing beforehand, decreasing after, it's changed direction. It's decreasing beforehand, increasing after, your graph has changed direction at that point. So critical points are points where your function may change direction. So if you look underneath here, there's some examples of critical points. Now these are critical points. Look to the left. These are stationary critical points, right? You get a horizontal tangent line at that point. But you're not going to get a relative min or a relative max at that point. Why not? Because your function's increasing up to that point, but after that point, it continues to increase. So for this one, right, the same thing. It's a critical point. It's stationary, right, because it's got the horizontal tangent line at X naught. But it's not a relative max or a relative min because it's decreasing up to that point. And, you know, it's decreasing after that point. There's no change. So there might be a change of direction. There's not necessarily going to be a change of direction. Here we go. We got vertical tangent lines here. Get a vertical tangent line here at X naught. So what does that mean? It's a critical point, but it's a non-stationary critical point, right? Because the first derivative is undefined, right? It's the slope of the tangent line. It's undefined at that point, so it doesn't exist. And again, it's not a relative max or a relative min because, you know, it's just, in this case, for this one, it's increasing up to that point, increasing after that point, so there's no change in direction. Here, for this one, it's decreasing up to that point, continues to decrease after that point.